This video is going to review the second half of our thermo unit. And a lot of this is actually going to be about kinetics, which is the speed of a reaction. But first we need to talk about collision theory, which says that in order to react, two things have to happen. First, you have to have enough energy. So if the particles are moving too slowly, they won't get over the hill for the activation energy and they won't be able to turn into products. And the second thing is you have to have the correct orientation. So it's pretty specific how particles have to interact in order for them to actually react. So in order to speed up the rate of a reaction, if you could increase either one of these two, if you could increase the amount of energy that products have, the reactants have, or if you could change the amount of energy required, or if you could change the amount of times that they collide so that you get more effective collisions, it will react faster. So in order to increase the rate of a reaction, you want to increase collisions. And not just any collisions, but collisions that lead to a product, so effective collisions. You could add a catalyst that will decrease the activation energy, so more particles will have enough energy to get over the hill. You could increase the temperature. That would give more particles enough energy to get over the hill, so more of them would be likely to turn into products. You could stir it, which would just create more collisions, so you're more likely to get more effective collisions. And you could increase the surface area. So that means breaking your reactant into smaller pieces so that collisions can happen on any side of those particles. If you have huge chunks of something, then the molecules that are in the middle of the chunk are not going to have access to collisions because they're stuck in the middle. So if you make smaller pieces, then you can have more effective collisions. All right, our next word is equilibrium. And this is kind of a big topic in chemistry. We only briefly touched on it, but you should understand what it is and how to write an equilibrium expression. So equilibrium says that the rate, which is your keyword here, of the forward reaction is equal to the rate of the reverse reaction. And we show this by doing a double arrow that's going to go forward and reverse. So when you're writing the equilibrium expression, so first of all, what I'm talking about here is that K fraction that we did. Make sure you know that products go on top and reactants go on the bottom. And in the reaction, again, reactants are on the left and products are on the right. You're going to raise these to the power of their coefficients. So if they have a number in front of them, those are going to become their power. Make sure that you don't include solids or liquids. You're only going to include things that have AQ or gases. So make sure you can write that for a reaction. Let's just do an example real quick. So if you had 2A plus 3B yields 4C plus 5D. Assuming these are all either gases or AQ, we're going to put C and D on the top because they are products, and we're going to put A and B on the bottom because they are reactants. And then all of the coefficients are going to become exponents. So 3 for B, 4 for C, and 5 for D. And then if they give you numbers, then you just plug it in and you can calculate K. If K ends up being greater than 1, it means you have more products. If K is less than 1, you have more reactants once it's reached equilibrium. And keep in mind that temperature is the only thing that will change K. And then the last thing for this chapter is Le Chatelier's principle. And this says that reactions will shift when stress is applied. So what I mean by shift is that you can force it to go faster in one direction or another. So once it's at equilibrium, the forward and reverse are going at the same rate. But if you want it to go faster in one direction versus another, you can put stress on the system and cause that to shift. And when I say put stress, there are 3 things you can do. You can change the amounts of reactants or products. So you can add things, you can take them away, and this is, when we did it in class, we talked about the sand piles. So picture your hands as a sand pile, and one is going up, and remember it always shifts towards the shorter sand pile. The next thing is you can change the pressure. This is only for gases, but if you have gases, you can change the pressure. And this is where you're going to think of crowded or lonely. So picture the balloon. If you're increasing the pressure, picture that balloon getting smaller. So they're going to start to feel crowded, so it's going to shift towards the side with fewer particles. And then the opposite, if you decrease pressure, the balloon can get bigger, so it's going to shift towards the side with more particles. And when I say more or less particles, I mean the coefficients in the reaction. So for this one, you have to go to the reaction and look at the coefficients and compare their left side to the right side. And the last thing you can do is change the temperature. But before you can do this, you have to put it in the reaction. Sometimes it'll already be in the reaction. So if it has kilojoules in the reaction, or if it says heat somewhere in the reaction, then it's already in there. So you just treat it like a sand pile. But if the delta H is off to the side, so if delta H then a negative goes on the right, and positive means it goes on the left. So if they have like delta H equals positive 65 kilojoules off to the side, positive means it's endothermic, so it means heat is going in, so you're going to put the heat on the left side of the arrow, and then you can just treat it like a sand pile. And that's it for thermochemistry.